So before the break, we look at how to find the first moment of area at point B over here. Okay. So if I'm going to sketch a shear flow, okay, it's going to come down here, and then it's going left and right. And we want to find the shear stress at point B. So the shear stress at point B is equal to Vy over Izz Qz divided by T. So for this case, as I mentioned before, Vy over Izz are constant, so I'm just going to leave it as a constant down here. Qz is now 60 times 10 to the power minus 6. The thickness now, right, because our variable y stop at here, you draw a straight line across, it cut across how many thickness, 1 or 2? 2 thickness. So you have to consider left and right. Webs and divide by the thickness of 0.02. So this will be equal to 60 power minus 6 divided by 2 divided by 0.02 is equal to 1.5 times 10 to the power minus 3 Vy over Izz. Okay. So knowing that Vy over Izz is constant, so from here we know that knowing that Vy over Izz are constant, the Qz over T ratio determines the shear stress distribution magnitude. Okay. No wonder I feel weird. The table was too high. Right. Now we're going to do a step further. Okay. Now all these examples has its meaning. Okay. Think of what I'm trying to do over here. Now the next thing I'm going to do is we are now going to determine we're going a step further. Today I'm a very happy man. Not that I had a baby or what, but a student come and told me that he got a job because what he learned from here. Okay, I'm not holding back. Okay, I'm going all out with you guys. Okay, that is the best news I ever had. You guys have blessing from what I teach. The rest, I don't give a toss. Now, what if now we want to find shear stress at the centroid? Repeat again. What if now we want to find the shear stress at the centroid? Okay, there are 2 ways that we can do this. There are 2 ways. Because of the rules that we have set, we can do this in 2 folds. Okay, so I'm going to show you method number 1, and I'm going to show you method number 2. Okay, so method number 1 is we are going to focus on the, I'm going to call this top section, and I'm going to call this side bottom section. Hey, too excited again. Okay, so we are first going to determine how centroid, okay, using the what? top section. Okay, we're going to use the top section. So this is the point. I'm going to change color. This is the point of interest now. Okay, now that's our point of interest. So we are going to focus using the top section. So the area to consider is this area over here together with this area over here. Okay, so I'm going to call this flange. This part against our, come on, why are you doing this to me? Flange, really, Eugene? This part is known as our flange. Sorry. Hold on, there's something going on with my computer. So this part is called my, It looks like someone is controlling my computer. No, let me close it first. Let me go back. Okay, I will not be so excited. So this is our flange. Oh, the gun. Wait. Something has gone terribly wrong with my figures. Yeah, it gone wrong forever already. It's okay. Okay. Come on, Eugene, move this. Technical difficulty. Pardon me, okay? Right. And then this one should be here. Okay. See whether will this work. I have to move this further up. And then I'm going to move this back. And I don't want to waste your time anymore. If I can't get it sorted out, we go home. I'm just kidding. So this is our flange. Over here, this is our web. Okay. So we are going to calculate the QZ. Oh, come on. QZ for the flange. So this is equal to width d y bar. The width is 0.16. The depth is 0.02. The y bar is equal to 0.035. So the y bar is basically the position of the centroid minus by you take this, you bring it over here, 0.02, and then you divide by 2. Can you see that? All these are pattern. That's why do not stop playing Nintendo. 10 by 0.02 times by 0.16 is equal to 80 times 10 to the power minus 6 meter cube. Let me do it again. I think we did this earlier, but I know it's correct. Then the next one, we are going to calculate the QZ for the web. So again, is width, depth, y bar. Now you have to consider the 2. The 2 is because you have a left web and you have the right web. And we know the distance from here to, come on, G, really? We know the distance from here to here is 35 millimeters. I'm going to sell all my stocks on Microsoft. I hadn't bought enough. Or is it the user? Okay. So the width is equal to 0.02. The depth is now what? 35 millimeters minus by what? 20 millimeters is equal to what? 0.015. Now the y bar is equal to 0.015 divided by 2. So this is equal to 0.015 divided by 2 times by 0.015 times by 0.02 times by 2 is equal to 4.5. times 10 to the power minus 6 meter cube. Let me do it again. 0.015 divided by 2 times by 0.015 times by 0.02 times 2 is 4.5 times 10 to the power 6. So we know the QZ from the top section is equal to 80 times 10 to the power minus 6 plus by 4.5 times 10 to the power minus 6. So this is equal to 80 plus 4.5 is 84.5 times 10 to the power minus 6 meter cube. This is by looking at the where? The top section, right? Why we can get it from top section? Because the analysis starts from, oh, come on. The analysis starts from, sorry. The analysis starts from where? Y max from the where? From the top. What if we do from the bottom? The answer will be and shall be the what? The same. Now, if we take it from the bottom, if we were to take it from the bottom, this is our Y max, right? So this arrow means our analysis really our okay, I'll slow down. This is our analysis direction. This arrow represents the analysis direction. This arrow represents the analysis direction. Oh, when I write slow, it works. Okay, so now if we were to consider the what? If we were to consider the bottom, section, right? Now we look at the first moment of area. So the moment of area, the area that we have to focus on is this area over here and this area over here. Okay, so over here, QZ, we focus on the bottom. So this is, so we have to do 2 because of the left and the what? Left and right. Okay, the width is equal to 0.02. The depth is equal to, so we know that the entire length over here is 65 millimeters, 0.065. The Y bar is 0.065 divided by 2. Okay, so I will write this. This is your left and right. This is your width. This is your depth. This is your Y bar. So this will be equal to 2 times by 0.02 times by 0.065 times by 0.065 divided by 2 is equal to 84.5 times 10 to the power minus 6. So for this case, the shear stress at the centroid is equal to Vy over Izz multiplied by 84.5 times by 10 to the power minus 6 divided by twice. The thickness is equal to 0.02. This will become 84.5 power minus 6 divided by 2 by 0.02 is equal to 2.1125 times 10 to the power minus 3 Vy over Izz. Now this value you see over here and this value you see over here, are they the same? Yes or no? They are exactly the what? The same. So either you want it to take from the top, from the bottom, you decide. Which one will you do? Bottom. Because bottom, you have less what? Component. Now, by looking at the top, if you take the top, you have to consider, a lot of time students make mistake, is you not just have to consider this area, you also have to consider this area. Are we clear? Okay. So that is important. Bottom, you only need to consider the what? You only need to consider the bottom section. Okay. I like to drive the importance again of the QZ over T ratio. That will help us determine where the maximum shear stress will be. Okay? It's both dependent on the what? The first moment of area. The bigger the first moment of area, if thickness is constant, the bigger the first moment of area, what happens? Bigger the ratio. Okay? If QZ is constant and T now is what? Smaller, the higher are your what? Stresses. Don't look at equation like that. You have to talk to yourself. Are we clear? You have to speak to yourself. I'm not crazy, okay? But you have to talk to yourself. What does it actually mean? What? Are we clear? Okay. Now, next thing. Are you all comfortable with this now? Yes or no? Okay. In order to do this, well, okay, I'm going to write short note for you. Number one. What is number one?